Hi everyone, my name is Eoin Carolan and I'm a PhD student in the Control and Thermodynamics of Quantum Systems group at UCD. I'd like to thank the organisers for allowing me the chance to talk about some upcoming work I have done alongside Anthony Kiley and Steve Campbell, my colleagues at UCD, where we look at kind of efficient counterdiabatic control for critical systems. So first of all, we're going to look at coherent control. So this coherent control of many bodies is needed for a lot of quantum technologies such as adiabatic quantum computing, quantum state preparation, quantum metrology, etc. So we can rely on kind of adiabatic methods, these slow external changes of your control parameters. But particularly for many body systems, you can lead to quite long timescales to reach the result you want. So a family of kind of shortcuts to adiabaticity have been kind of proposed to achieve high fidelity, if not perfect, control at a significant speed up. And for kind of a great review and kind of well-cited review of this, I'd point to work that one of my colleagues has worked on as well, cited below. So the particular shortcut to adiabaticity we look at in our project is counterdiabatic driving. So this kind of reverse engineers to allow you to follow the instantaneous adiabatic eigenstates of the system Hamiltonian that you're interested in. So for some generic kind of reference Hamiltonian here, diagonalized, we can write a counterdiabatic term, which kind of recreates both the dynamic and geometric phases of the adiabatic state you're trying to follow. So we evolve the state with both H0 plus HCD. As this is an additional kind of Hamiltonian term, it implies an additional cost to evolving the system, as discussed in the review I'd cited previously. So this kind of begs the question whether we can reduce the cost of this counterdiabatic control while still achieving high fidelity final states for critical systems. So there's some intuition from the Kibble-Zurek mechanism, which describes the dynamics of non-equilibrium phase transitions. So the Kibble-Zurek mechanism relies on having nearly adiabatic ramping with the kind of non-adiabatic effects coming from the presence of a critical point or critical points. So it describes like a continuous phase transition. So it was originally proposed by Kibble in a cosmological context for the symmetry breaking and domain wall formation of scalar field theories. And then Zurek applied it to condensed matter critical systems. But importantly for us, yeah, it divides the evolution of your system into an adiabatic and impulse regime. This image I've pulled from the thesis of Ricardo Puebla. So the energy gap delta of our system between the ground state and the first excited state sets the time scale for the ability of the system to heal to external changes of your control parameter. So in this work, we look mainly at linear ramps. And so the important quantity here is the relaxation time, which is the inverse of the gap. And so as if the relaxation time is smaller than the rate of change of our ramp, the system can easily react to these changes and we don't see the formation of defects. Whereas if the relaxation time diverges as the gap shrinks, it can no longer react to these changes and the system state is effectively frozen. So from this, we can define two times by equating the relaxation time to the rate of change of our ramp, where GC is the kind of critical value of our ramp. So again, yeah, to summarize that again, yeah, so far from the critical point, we have adiabatic evolution. The relaxation time is faster than the rate of change. And near the critical point, it can no longer react to the change. We have this impulse-like behavior. So this implies that we mainly require control in this impulse regime. That's where probably wasting resources on trying to control the system far from this regime, we would get adiabatic-like behavior for free. So if this is the case, how high fidelity are our results, and how much do we reduce the overheads by? So we first look at this Landau-Zener model. And so even though the Kibble-Zurek mechanism is for critical systems for which the Landau-Zener is not, it has an avoided crossing, not a critical point, it still captures the dynamics and the characteristic scaling of the Kibble-Zurek mechanism, as shown by Bogan-Damsky here. So we have this two-level system. Again, we have this linear ramp. We ramp from a negative value initially through this avoided crossing, which we put at g equals 0, through to some positive value. Again, we have some off-diagonal constant coupling term. And the interesting thing for the Landau-Zener model here is that the density of defects is analytically known for uncontrolled evolution. So we can compare it to that. So again, we use this prescription from the Kibble-Zurek mechanism. We can define some crossover times. So this is for a single evolution of our Landau-Zener system. So our relaxation time diverges around our critical point, but halfway through the evolution, and divides it into these two regimes, adiabatic and impulse, and adiabatic again. And here for a range of different lengths or slope ramps, taking delta equal to 1. So for very kind of short and rapid ramps, almost the entire dynamics of our protocol is impulse-like, whereas as we get very long evolution times, almost all the systems evolution is adiabatic as expected. So this kind of leads us to see if we can bring in this protocol where we let the system evolve adiabatically until we hit this crossover time, where then we will bang on this counterdiabatic control term to freeze transitions or non-adiabatic transitions between the crossover times, and then we turn off the counterdiabatic control afterwards. So we call impulse-only control. So again, we have shown here green is full control, which achieves perfect fidelity all the way through as expected. Impulse-only control shown in red, and the uncontrolled evolution shown in blue. These are just for a single evolution of the system in each case. So we see for this kind of impulse-only control that the fidelity of the system follows that of the uncontrolled case as expected. And when we bang on this counterdiabatic control term, it freezes transitions. We get this no population transfer in this impulse regime. And then we see this kind of curious recovery when we allow the system to evolve adiabatically freely again. Again, for this very long evolution, even though the impulse-only control doesn't actually outperform having no control, we again see this adiabatic recovery, which is a kind of curious phenomenon which was discussed by Ben-Senior and Milner in a recent paper. So this is a where the time evolution of a state can deviate from the adiabatic eigenstate and still find its way back to a higher fidelity towards the end. And so for a range of different ramp lengths, we show the final state fidelity or infidelity in this case. We see a sort of sweet spot. In red shows where we use this kind of impulse-only control, and this blue line is just the free adiabatic or diabatic evolution as described by the analytic Landau-Zener formula. So we have a sweet spot that's dependent on our initial kind of ramp value that moves along. But again, we have like almost near perfect final state fidelities for this sweet spot. So that's kind of the first part of what we wanted to see kind of ticked off, that we do achieve high fidelity results, but how much do we actually save? So there's many ways to measure the cost of counterdiabatic control. a lot of which is discussed in the initial review paper I'd cited. But we use in particular this trace norm measure, time average trace norm measure proposed in this paper here. It relies only on the counterdiabatic term itself to measure the costs. So we measure both the absolute cost and the relative cost. The relative cost compared to the typical way of using counterdiabatic control, which is to leave it on throughout the entire evolution. So using the same values where we've seen this sweet spot before, around tau cubical 5, we have almost 40% relative savings at a basically perfect fidelity final state. And so moving on from that, we looked at the transverse field Ising model. We employ this Jordan-Wigner transformation to decouple it into n/2 Landau-Zenner problems, taking only the positive parity subspace and even boundary conditions. So the lowest subspace here is critical. Again, we ramp it linearly, placing the critical point halfway through the evolution. Instead here, now the critical point is at 1, GC equals 1 instead of GC equals 0. Again, we see the same qualitative behavior where we see a huge increase in the number of defects for the uncontrolled case in this impulse regime. This characteristic freezing when it's only controlling the impulse regime, and perfect control when we employ counterdiabatic control the whole way through. And here, the blue line shows the final state fidelity for impulse only control versus the totally uncontrolled case. So for long times, we do expect both to go to perfect fidelity as kind of imposed by the adiabatic theorem. And again, we see high fidelity results with significant relative savings. So here is the relative savings for different lengths of chains and absolute savings as well. So to conclude, by exploiting the framework provided by the Kibble-Zurek mechanism, we show that by suppressing transitions in the impulse regime, the system is free to undergo the natural recurrence that adiabatic processes can entail. This high fidelity coherent control can be achieved at a lower energy overhead than the typical use of counterdiabatic driving.
Thank you. That was a great talk.
Thanks very much.
Do we have questions in the audience? Yeah. Perhaps I can start. Can you say a few words about how universal this picture may be? I mean, if I understand you correctly, you're basically applying your counterdiabatic control mechanism only in very particular phases of the time evolution, and this is how you get the energetic cost. But is that a universal feature, or is it tied to these Landau-Zenner type problems?
So I think the Landau-Zenner, so it's applied to anywhere where the Kibble-Zurek mechanism can be applied to, for which the Landau-Zenner is probably the simplest model that it can be applied to. So the kind of interesting thing with the Kibble-Zurek mechanism, it has all this kind of universal critical behavior. So I'd assume that any kind of system that follows or is not the same sort of universal like a renormalization group class should have the same characteristic behavior.
Okay, thank you. Paul has a question. Paul, do you want to ask yourself?
Sure, I can. So I was just wondering about the cost function that you define and what the operational interpretation of that is.
I don't actually understand this question.
Okay. So right here, the slide that you're on. Mm-hmm. So you're looking at this integrated trace norm of the counterdiabatic Hamiltonian, and I'm wondering kind of physically why we should understand this as a cost. I guess it requires some kind of abstract notion of resources to apply, or is it like a matter of effort, or in what sense is this a cost? Is it energetic? Are we draining a battery, for example?
That's quite interesting. I'll have to kind of do a bit more reading on this particular kind of cost function. I just assume that just the dimension, that like the dimensions of the Hamiltonian being energy, that we can just take the time average of it, taking some sort of norm.
Yeah, I mean, I have seen it used a bit recently, which makes me even more curious about what it's good for. Okay, yeah, well, thanks.
Thank you.
Okay, Asan has a similar question. Do you want to elaborate on this, Asan, or do you get your answers?
I don't know if it's worth elaborating much more on it. I just thought that eventually one would get back any extra energy that was put in, because you end up in the same state with the same Hamiltonian at the end of the protocol. So I've never really understood the sense in which these are costs in that sense, in these kind of shortcuts. But
You said that the counterdiabatic term just disappears at the endpoint.
Yeah. So to me, that seems like whatever energy you're investing, you're getting back again by the end of the protocol. But of course, I mean, in the presence of noise or something like that, then maybe there is an extra cost because the amplitude is increased, and so fluctuations, perhaps if they're proportional to the amplitude, will increase as well. But more generally, I guess it's similar to Paul's question. I don't really understand the nature in which these quantities are meant as costs.
Okay. Camilla has another question. Do you want to ask yourself?
Yeah, okay, yes. No, so yeah, thank you for the talk. It was quite interesting. And my question was, so you use the counterdiabatic driving, but there are a lot of other similar driving, so trying to reach, to get the same result, but using a different dynamic. Do you think there could be other driving leading to a lower cost, or have you looked at that question, or yeah?
I think it's not a question we've looked at yet, but it would definitely be a place to go to next to start looking at like local counterdiabatic driving, in particular for the Ising model, because the counterdiabatic term that we use there is like highly non-local when you take this Jordan-Bigner transformation. So you could do it only like a local or two-body control. I think is more implementable, and would be kind of more interesting to look at that. And to look at then, as you're saying, different ways of implementing counterdiabatic driving. So I think the Ben Selmy and Milmer paper look at this kind of super, so they're looking at counterdiabatic driving in this super adiabatic basis, where I think that, if I can get to it here, kind of the main explanation of this recovery is that like these kind of defects that are first order in kind of the inverse lengths of your quench disappear at the end of your ramp, whereas the second order ones do not. And so they use this counterdiabatic control for the second order stuff to achieve kind of very high fidelity results. But this is not just in the impulse regime, so it'd be interesting to look at that as well.